Good afternoon, chemists. Hopefully you're doing well. Trying to find the best ways to kind of record some of these short classes. Try to keep them short and sweet with the background information you need to be able to do the assignment, as well as some good practice examples of the assignment as well, so that you should have all the information you need regardless if you have your textbook or not. So we're kind of coming, this is our last topic of the unit. Next week or in the next 2 weeks, we may have some sort of short online quiz for different topics that we've looked at for this unit. Trying to think of the best way to do that. I think the best way to do that is probably to use cumulative or highlight problems from your textbook. Not ones that really have some specific skills, because then you could just kind of look those up on the internet, but ones that you'll really have to kind of combine your knowledge for, and there can be a variety of acceptable answers, that kind of thing. So we're going back to one thing that we've talked about at the beginning of the unit, which now is stretching way back to, I don't know, beginning of March maybe. But we're going to talk about types of solids today, and whether they're molecular, ionic, or atomic, and what you need to do, your objective, and sorry I don't have that written here, I'll write it here now. Your objective, what you need to do with this information. I like to write things out beforehand now, because I can write things out much neater when I'm not trying to look through a screen. Your objective is that you need to be able to kind of order and rank melting points of solids. And that's what we're looking at today. So at the end of it, you should be able to say, I can rank or order melting points of solids. And again, this will relate to both the kind of solid they are, but also the kind of intermolecular forces that make up the solid. I can or I can't. And then if you're looking at it that I can't, then either you need to ask questions when we meet tomorrow on Wednesday, or I'm having, this week we're starting general office hours on Friday. I believe it's Friday right after lunch. It should be on your schedule. And there'll be on the chemistry page, there'll be a meeting link that's posted. You don't have to go to that, but if you're having trouble, you really should come in and do that. Okay. So types of solids. So if we go back to our beginning of our unit, there are two main types of solids. What we're going to talk about today, the main type that we care about, are things that are crystalline solids. And that anything with a crystal means that it's fairly well ordered. There's an order, there's a pattern. So if we think about diamond, all those carbons that make up diamond are very well ordered into a crystal, like a lattice structure. The other one that means no shape or no form, and by definition disordered, these are amorphous solids. So an example there might be something like sugar or something. The sugar crystal is not as well ordered as, say, the salt crystal is. Okay, we're going to mostly look at the crystalline ones today. Okay, crystalline solids. We can put crystalline solids into three main categories. Okay. And each category is going to have a slightly different melting point, because the intermolecular and intramolecular forces that hold the atoms together, the atoms or the molecules together in their crystalline lattice structure, will be slightly different. Some forces will be stronger, and the stronger the forces, the more energy that's required to break bonds, so the higher the melting point will be. The weaker the forces that bind molecules or atoms together, the less energy that's required to pull them apart, so the lower the melting points. That's the main idea of all of this. So the first one we'll look at are the molecular solids. And I hope, going back to the beginning of the year, we remember what the word molecule refers to. And in some ways we kind of think of molecules as being everything kind of in chemistry, but that's not really true. We need to think of the difference between things like molecules and other kinds of compounds. So a molecule usually, right, refers to two nonmetals that are bonded together. Two nonmetals. The units that make up a molecular solid, these are, of course, molecules. So these are two nonmetals that are bonded together in some ways. Covalent bonds, molecular solids, right? When we have two nonmetals together, they're going to have sharing. They're going to share their valence electrons. And so they're going to have covalent bonds. And those covalent bonds, right, depending on the electronegativity differences, can have more of a polar covalent character or more of a pure covalent character. But these are characterized by low melting points. Okay? For example, ice. Right? The melting and the freezing point of ice is, of course, 0 degrees Celsius. Dry ice, which is carbon dioxide in a solid form, it, to be fair, doesn't really melt. It doesn't really become, carbon dioxide doesn't really become from a solid to a liquid and then to a gas. It's a solid at very, very low temperatures. So when people use it, like in effects, like any of the classic science movies, why are things bubbling and frothing? Because they use a lot of dry ice. On a lot of stage shows, they use dry ice as well. That isn't really melting. That's what's, and you should know this term, right? It's sublimating. So the process of sublimation means we go directly from a solid to a gas. And so you can, that's why it's all kind of white vapor, because you can see it turning directly into a gas. And it does this, of course, at a very low temperature. That's why when you get into room temperature, it's very readily turning into a gas. It does it naturally at minus 78.5 degrees Celsius. Okay? The second kind of crystalline solid are the ionic solids. Okay? The units are the formula units, and we can think about, well, again, everybody should know what an ion is. I really, really hope this time of the year everybody knows what an ion is. But in case we don't know, an ion is an atom that has either lost or gained electrons, right? Remember, atoms can lose or gain electrons and still be considered the same atom, or they can lose or gain neutrons and still be considered the same kind of atoms. They cannot lose or gain protons, because by definition, then, they would be a different atom if they did that. Okay? So one atom, say a gold atom, can lose electrons and still be considered a gold atom. Why? Because it still has the same number of protons inside. But it's going to then have a positive charge. Positively charged ions, as you remember, this is review, are called cations. Meow, people like cats, so I guess they're positive. That's maybe how you can remember it. An anion, I don't know, Annie was the character, Anakin Skywalker from the prequel trilogy of Star Wars movies. Those were horrible movies, very negative. That's what makes me think about it. Or really the way I think about it is anion, the word Annie sounds like the Korean word for no. So it's negative in that sense, like a negative ion. Ionic solids, as we remember, things that are held together through ionic forces, these are electrostatic forces. These are pure Coulombic, and if you go into AP chemistry, almost every answer, and it's kind of a joke, can almost be answered by saying Coulombic forces. And Coulombic forces are just forces of electrostatic attraction. So how positive or negative something is to bring the two things together, much like the way a magnet works. And so these things are held together with extremely strong forces, and stronger ion forces mean higher melting points. So if we think about it like salt, right? And so salt dissolves very readily in water. And we need to be very careful that the idea of dissolving is not the same idea as melting. Okay? Because we should know basically what the idea of dissolving is. Okay? That's when it breaks apart, it disassociates in a liquid and becomes surrounded by the other molecules. That's the process of dissolving. Melting, right, is the process of turning a solid into a liquid. So if you want to create liquid salt, this is not the same thing as salt water. Liquid salt, you need to use an incredible amount of energy to break those electrostatic forces. In fact, you would need 801 degrees Celsius to melt salt. So that's quite a bit. When we compare that with water, right, when solid ice melts at 0 degrees Celsius, that's a large difference. Okay, why? Because of the strong IMF. Okay, so far we have molecular solids. They have very low melting points. Ionic solids have very high melting points, and because it's chemistry and nothing is as straightforward as saying, okay, just memorize this one is high and this one is low, there are always a ton of exceptions, but hopefully exceptions that make sense when we think about the explanation in chemistry. So there's one more kind of solid called atomic solids. Okay, you may have been thinking, well, iron. You've seen iron in the lab. Iron is an atom and it exists by itself as a solid. In reality, it has other things bonded to it, like oxygen and different things. But if we get pure iron, like the kind that we use in the lab for our experiments, iron filings, this is an example of an atomic solid. So it's many kinds of iron atoms that are bonded together. Okay, so the units here are atoms. The units in molecular solids were molecules. And ionic solids were cations and anions. And for these ones, they are just atoms. And usually these things by themselves, when they're like this, are just metals. And a lot of them are transition metals too, is how they kind of work. Now, to make this more difficult, there are different flavors of atomic solids. Okay? There are 3 different flavors. There's one that's covalent atomic solids. So these are ones these are atoms they're metals, but they're bonded together covalently. So something like silicon. And then these ones, comparatively speaking, have fairly high melting points. So silicon, for example, has a melting point of 961.8 degrees Celsius. If we think about diamond, which is very similar to silicon, it has a similar melting point as well. Very, very high melting points, right? Diamond is very, very strong. What is diamond? Well, it's just a lot of carbon atoms put together in this lattice crystal structure, all sharing their electrons covalently with each other. Silicon, which is structurally similar to carbon, does the same sort of thing. Now, there are ones that are non-bonding atomic solids. Okay? These are things that you can think of these things mostly as they exist in gas form. But if you get them cold enough, right, anything you can turn into a solid, liquid, or gas if we subtract the right amount of heat energy or we add the right amount of heat energy to it. So for these are things that normally want to exist as gases. You can think of these things as not being metals, but these are the noble gases, usually. And they have very low melting points, right? So if we think about something like xenon, right, is a noble gas. It melts at minus 111.8 degrees Celsius. That means that lower than 111.8 degrees Celsius, it exists as a solid. So xenon, right, in room temperature where you are right now exists as a gas. So if you want to make it a solid, you need to get it really, really, really cold. Okay, these have low melting points. Okay, the last one are metallic solids. Okay, and they have, to make it trickier, they have variable melting points. Variable means it can change. Some are high, some are low. Okay? Now, these things have a form of bonding which we did not talk about. We did not talk about the theory behind metallic bonding, and I'm not going to go into it too much because it's not overly important for us. But metallic bonding follows what's called the sea of electrons idea. The sea of electrons. So what does this mean? Well, we've got, let's say this is the nucleus of a gold atom. We've got a nucleus of another gold atom, and a nucleus of another gold atom, and a nucleus of another gold atom, and a nucleus of another gold atom. What happens is that the electrons, right, of course, are very negatively charged, and there aren't enough. So some of them leave one, and it becomes more positive here. So some of them get pulled over here, which makes this one more positive here, which pulls electrons off from over here. And you can imagine this as one electron is constantly being pulled off and another atom is getting a positive charge, which is pulling off an electron in another part. What we do is we end up having what's called the sea, the ocean, a sea of many electrons that are constantly flying around all of these different atoms. In a way, this is what metallic bonding is, that can link them all together this way. So something like gold or iron, this is how they're linked together. This is how we have iron in the lab. These are all individual iron atoms, and they're all being bonded together and linked together into a solid format by these free-floating electrons. And this is what's known as the sea of electrons theory. And this can create some that are very high melting points, and some that are very low. So for example, gold, for example, has a very high melting point. It stays solid pretty readily, but it melts at 1064 degrees Celsius. Okay, so the sea of electrons confers kind of varying strength to the different atoms. Okay, so that's the idea behind this. So we need to consider this with different strengths, the different IM forces, and the different types of solids and the IM forces when we're solving these problems. Okay, if you do have your textbook, these problems are found on page 440. I want you to do question 80, but I'm going to give you an example which is the same idea as what's in the book. So that would be question 79, which is similar to 80. So it says that we need to determine what kind of solid is it, you need to say. So the first one, AR, and of course we need to know these things. And again, this is a wonderful opportunity if you still haven't learned common elements from the periodic table or polyatomic ions. Please use this time to really go through and memorize some of these things. You really need to know what they are in English if you're going forward and studying this. Okay? AR, so what is AR? AR is argon, right? Why didn't the chemist tell any jokes? Because all the good ones are gone. Argon. Okay, Cue the laughter. So what kind of solid is it? Well, argon exists by itself as just one kind of atom. It's a noble gas. So it's one of these. It's an atomic solid. It's just one of these. Okay? And in fact, it's going to be, if you want to get more specific, which you don't need to do to answer this question, it would be an example of a non-bonding organic, a non-bonding atomic solid. Next one, H2O solid, ice. What kind of solid is that? Well, what is hydrogen? What is oxygen? These are two nonmetals. Two nonmetals bonded together. This is an example of a molecule. So it's a molecular solid. The next one, K2O. K is a nonmetal, and K is a metal, and O is a nonmetal. This is potassium oxide. You should be able to read these. Potassium oxide. Okay, so we have a metal, potassium, and a non-metal oxygen. So this makes up an, you guessed it, an ionic solid. The last one, iron. Okay, iron, we just talked about this one in one of our other examples. Iron is an example of an atomic solid. And if we want to really get specific about what kind of atomic solid it is, then it would be one of those ones that use, it's a metallic atomic solid. It's one with the variable melting points. Sea of electrons theory. Okay? So I'd like you to do 80, question 80. It's the same idea. Okay. Now, here's something which is important for us. So the next question is number 85. I'm going to go through this with you, and then I want you to do number 86, which is the same idea. So 85 says, which pair, so it should be which member of the pair. So which one in the pair has the higher melting point? And then, of course, the most important point, explain why. A lot of you, for your work, will just give an answer about which one, and then there'll be no explanation about why. Okay, this why is important because this is how we can argue about things. Sometimes I'm wrong. Okay, titanium and neon. Well, which one is higher? I'll give you a second, you can think about it. First of all, you should be thinking about, what kind of solid it is, and then what kind of ion forces might it display, because that will help you. Well, these are both individual atoms. So the answer here is titanium has a higher melting point because metallic atomic solids, that's what it is. It's an atomic solid. It's a metallic one. Is higher than neon because neon has weak dispersion forces. Okay. Neon is a noble gas. If you want to make neon into a solid, you need to get it at an extremely low temperature. Titanium is already a solid. Neon's a gas. So we can already, you can think about why that is. Well, the reason why that is because of the intermolecular forces that are different between titanium and neon. Neon, if you want to make it a solid, you need to really cool it down, slow down those atoms so that they come closer and closer together, and usually give them some higher pressure as well. And then they will bond together, but the only forces that will help them bond together are those very weak London dispersion forces, which are the weakest ion force of all, because they just result from the random kind of fluctuation of electrons in the probability cloud. Okay, that is a nice complete answer. Okay, the next one, B. Which one shows a higher melting point? Is it solid water, ice, or is it H2S, which I hope you could read? H2S, hydrogen sulfide. Hydrogen sulfide is what its common name is. Okay, so if we look at both of these, okay, they both, before I show you what the answer is, let's go through some of the thinking. Well, the first thing is, what are we dealing with here? Well, hydrogen's a nonmetal, oxygen's a nonmetal. In hydrogen sulfide, the hydrogen, again, is a nonmetal, and the sulfur's a nonmetal as well. So we've got something that's covalently bonded together. These are both of them are molecular solids. So we can't really determine what the melting point will be in a kind of rank order just on the basis of what kind of solid it is. So we need to go back and think about what IM forces. What are the intermolecular forces that exist between water and hydrogen sulfide? Okay, well, both of them are going to have dispersion forces. Okay. Both of them are going to be polar molecules because there's a huge electronegativity difference between hydrogen and oxygen and hydrogen and sulfur. So they're both polar. Okay? They're going to have roughly around the same kind of molecular weight to them. There's one difference that separates them though. And it has to do with water. Water has something that hydrogen sulfide does not have. Ooh, I know, Mr. Harrison, I know. Yes. Water has hydrogen bonding, which a hydrogen bond is stronger than just a dipole-dipole. So, which one has a higher melting point? Water has a higher melting point because of hydrogen bonds, which are not found in hydrogen sulfide. Okily dokily? Okily-dokily. Okay, our last two. We have krypton and xenon. Krypton and xenon. Well, let's go first. What kind of solids are we dealing with here? This pause is not for dramatic effect. It's hopefully giving you a bit of chance to mull it over and to think. Well, krypton and xenon are both by themselves. If you look at the periodic table, they are both, actually I've got my periodic table right here. Okay, krypton, xenon, they're both on the periodic table. They're both noble gases. Okay, so they both want to exist in a gas form at kind of room temperatures. Which means, again, if you want to turn these things into a solid, it's possible, but you're going to have to really decrease the temperature, meaning you're going to remove a lot of energy, and maybe increase the pressure as well. Now, so how do we determine? Well, then what kind of intermolecular forces do krypton and xenon display? Well, the only intermolecular forces that these two can display are London dispersion forces. Well, the one with the stronger dispersion force then is the one that's going to have the higher melting point. So how do we determine which one has a stronger dispersion force? Again, this is not for dramatic effect. It's hopefully giving you a chance to think. The one with the larger dispersion forces is going to be the one with the larger molar mass. Which one has a larger molar mass? Because in some ways, it's just going to have more electrons that are available to fly around, so there's more chances of creating those kind of induced instantaneous dipoles that are characteristic of London dispersion forces. So again, if we look at our periodic table, which one has a higher molar mass? Well, xenon does. It's 131.29 grams per mole compared to krypton, which is 83.798 grams per mole. So which one has a higher mass? A higher melting point? Well, xenon has a higher melting point because, and again, we never start sentences with the word because. Put Mr. Harrison in a bad mood quickly. Keep starting your sentences with the word because. Xenon has a higher melting point because it has a stronger dispersion forces that are found in larger atoms. Why do larger atoms have stronger dispersion forces? Because they have more electrons. More electrons means more random movement, more possibility that they can clump together, creating an instantaneous dipole. Okay, so you need to do question 86. So you have 2 questions for homework. You have question 80 and 86. That's not very long, and you should be able to do it on time. Okay? If things are late, you're kind of losing marks now, because there's no excuse for things to be late. Because you can ask me questions during class. You can email me questions at any time, because I'm locked down, I'm not going anywhere, and I'm still teaching and working during the day. And now we have office hours that are on Friday as well. The other thing that we're still not doing is turning in our class notes immediately after the class. Some of you I'm still having to email to remind you. This is losing you marks for doing this. Okay? All you have to do is turn it in right after class. Take a quick picture, hand it in. That's not hard. It shows me that you've been listening and thinking about what we're doing. And again, the purpose is not to copy everything down word for word, but it's hopefully for you to be able to summarize in your own words what are some of the key important points of the class. Because that summarizing activity of the key important parts of the class really helps you learn the material. Because if you have to be thinking all the time while you're trying to listen and write down, what's the most important thing that's here on the slide or that Mr. Harrison is saying, that deep thought helps you encode that information stronger in your mind than just passively copying everything down. That's why we do it. Is it harder? Yes. But things that are harder help you to learn. Okay. Got a little bit of an extra little rant today, and so I'm going to leave it there today. I think 30 minutes is a good number. Okay, stay safe, play safe. See you soon.